Good afternoon, everyone, and welcome to the Society of Wetland Scientists October webinar. My name is Sean Charles, and I'm your moderator today. We have a great turnout for today's event, and I'm excited to introduce our speaker for today's presentation. The general format today will be a 45-minute presentation followed by approximately 15 minutes for questions and announcements. Go to the next slide. So before we get started, I just wanted to talk a little bit about how this works. So let's familiarize ourselves with the GoToWebinar system. On the side of your screen, there's a control panel that looks like the example on the slide here. In the audio pane, you can adjust the webinar audio by using your telephone or computer speakers. At any time during the presentation, you can type your questions into the questions pane, but Matt will be answering questions at the end of the presentation. If you'd like a copy of today's slides, please find a PDF copy in the handouts pane of the control panel. As a reminder, webinar certificates worth 1 hour of participation are available upon request. Please contact the SWS staff if interested. Certificates are also available for those who watch webinar recordings. All webinars are recorded and archived for complimentary viewing by members on our past webinars page. This webinar is being recorded and you'll receive a link to the recording following the webinar. We also ask that you take a moment to complete the evaluation survey that will pop up at the end of the webinar. In addition, we encourage you to use the hashtag SWSwebinar on Twitter to tweet about today's webinar. We love seeing what you have to say. Now let's test the questions pane. And at the same time, get some demographics by having everyone type the state or country you are participating from into your questions pane, please. Oh, wait a sec. All right, we got Washington, we got Bangor, we got Florida, we got Seattle, Texas, Oregon, Georgia, lots of people. Okay, thanks everyone. Hi, Lori. We can go to the next slide. So it's my pleasure to welcome today's presenter, Matt Kerwin. Dr. Matt Kerwin is an assistant professor at the Virginia Institute of Marine Science, VIMS, with expertise in coastal geomorphology and ecology. His research focuses on Marsh response to sea level rise, carbon climate feedbacks, and the role humans play in the formation and survival of coastal landscapes. He's a graduate of the College of William and Mary, once again, a great school I hear, and Duke University, and a member of the Nassau-Wawash Indian tribe. Welcome, Matt. Thanks a lot, and I'll turn things over to you.
All right, thank you, Sean. Let's see if I have control of the slides now. I'm going to try to advance to the next one. All right, seems to be working now. I'm not real used to giving talks where there's no audience in front of me. It sort of brings back bad memories of practicing conference presentations in hotel rooms with just a laptop and a wall in front of me. So forgive me if I stumble about and if it sounds like a practice talk. That's because it in some ways it is. I want to start with this title slide showing two pictures basically of the same marsh. And I start a lot of my presentations with these two pictures because they illustrate a couple things. First, it's where this is the marsh where all my ancestors are from. And second of all, it shows really different ways in which marshes respond to sea level rise. If you look at the picture on the left, that's an aerial view, and you see a bunch of ponds in the foreground of the picture. Those ponds weren't there 50 years ago. They're a new feature. The marsh is rapidly submerging, eroding. Those ponds are getting bigger, and the marsh is being lost. This is near the Blackwater National Wildlife Refuge, which is a poster child for marsh loss and marsh drowning in response to sea level rise. It's a poster child. There's really no better example of it in the United States other than coastal Louisiana. Now, just in the background of that same photograph is where the picture of me and my two kids are. And that illustrates a really different way by which marshes respond to sea level rise. And if you were my kids' great-grandparents, the marsh behind them in large part wouldn't have been there at all. That was mostly forest, some agriculture. Strawberries were grown on a little bit of that marsh until about 50 years ago. And basically what that represents is a marsh that was actually created by sea level rise. So we're looking at the same place in these two pictures, just a couple hundred yards apart. One place the marsh is getting smaller because it's submerging and eroding in response to sea level rise. Immediately next to it, the marsh is getting bigger in response to sea level rise. And I think that kind of observation really frames what the goal of this talk is going to be. How marshes respond to sea level rise and why different marshes respond in fundamentally different ways. And I'm going to try my best to use examples, especially from around the Chesapeake, to explain these different in-member scenarios and the processes that are involved in either keeping a marsh stable or the processes that destroy the marsh. All right, so I'm going to go to the next slide. I think I can do that myself. There we go. All right, and this is the central question. Will coastal wetlands survive sea level rise? And I've included on the left a paper that was really helpful for me. This is one of the first papers that I really explored in depth when I was a graduate student, and it summed up many of the issues with trying to predict whether wetlands will survive sea level rise. And Denise Reed had a really interesting insight that I've pulled from the paper and highlighted at the bottom here. And Denise Reed basically said that the fate of wetlands depends on complicated ecological and geomorphic processes that interact with each other, and that it's nearly impossible to predict fate beyond the local scale. In other words, if you know a lot about one marsh and you try to predict the fate of another marsh, it's very difficult to do. So while that was what I thought was a really important conclusion of that paper, I'm basically going to ignore that advice completely for the rest of this presentation and try to, using a combination of observations and numerical models, try to make those predictions, try to predict why some marshes behave differently than others, and whether there are simple things that we can measure or observe that will tell us whether some marsh far from the local scale will respond. Salt marsh response to sea level rise is certainly complicated, and there are lots of different opinions on whether marshes today are surviving rates that we're already experiencing, and even more different opinions on whether marshes will, how they might survive or collapse under future rates of sea level rise. And so I've just pulled a couple different papers from the literature to illustrate the wide differences there are in predictions of how marshes and other coastal wetlands will respond to sea level rise. So you see in the top left corner, for example, 69% of mangroves in the Indo-Pacific are already submerging at current rates. Right below that, 60–90% of marshes global, I think that was North America, will submerge at future sea level rise rates. The paper below that suggests 50–80% of all the marshes in the world will submerge at future sea level rise rates. And then we've got two papers on the right that show that have a very different outlook. The one of my own suggests that very few marshes are currently submerging under current rates of sea level rise. And then the one in the bottom right says marshes, at least in this particular location, are actually getting bigger as a response to sea level rise. So I think that pretty well covers the gamut of possible outcomes. Will marshes get bigger, smaller, stay the same, and will that happen under current rates and under future rates? The message of this is that Coastal areas are very dynamic. They involve interactions between ecology and geomorphology that are hard to predict, and therefore the response to sea level rise is hard to predict. I do a lot of my work in the Chesapeake Bay, and one of the advantages of working in the Chesapeake Bay is that it's a big system. There are big marshes, and there are lots of different end members. You know, I feel like we don't have any macrotidal marshes, but other than that, you can pretty well run the gamut of different species and different geomorphic settings. There's lots of different types of marshes there. It also experiences some of the fastest rates of relative sea level rise anywhere in the world. Its local rates of relative sea level rise are about twice the global average. And as a result, we see examples of where marshes are submerging, like the picture in the upper right. On the other hand, we also see places like I showed you in the title slide of places where the marshes are getting bigger as they migrate into the uplands. And then finally, we see a lot of marshes that are just stable, and they look kind of the same in aerial photographs over the last 100 years. And so, again, I'm going to try to make some conclusions about why these different marshes operate differently, and then what that means for how we think marshes in other places around the globe might respond to sea level rise in some kind of coherent way. All right, so here's an outline of my talk. The first point that I'm going to try to make is that ecological geomorphic couplings, I'll call that ecogeomorphic feedback sometimes, tend to result in a situation where marshes are relatively stable in their vertical dimensions. In other words, that they build their own soil elevation at rates that tend to adjust to the rate of sea level rise, and so that the marsh maintains stability in the vertical dimension. And of course, I'll explain what those processes are and how that works. Then I'm going to talk about lateral changes in the marsh, where processes cause them to get bigger or smaller in the lateral dimension. And then finally, I'm going to try to wrap up the talk by considering how marshes respond to sea level rise in the absence of and in the presence of human adaptations to sea level rise. I'm thinking of things like land use change and especially flood control measures, building seawalls, things like that. And my ultimate conclusion will be whether marshes get bigger or smaller in the future under faster rates of sea level rise will depend not so much on the rate of sea level rise itself, but on how we go about influencing marshes more directly through flood control measures. All right, so that's the outline. I'll start with this first topic, which is the ecogeomorphic feedbacks tend to lead to relatively stable marshes in the vertical dimension. And the reason why that is true at its most fundamental level is that the more often the marsh is flooded, the more potential there is for sediment to settle out of the water column and deposit on the marsh surface. It works just like a river floodplain. Every time the river floods its banks, it deposits that great loamy soil that makes floodplains so productive. Same thing happens in tidal marshes that are dissected by tidal channels, except now instead of the river flooding its banks, once a year or something like that, the tidal creek is flooding its banks in many cases twice a day. And so you have an input of mineral sediment twice a day onto the marsh surface. The more often it's inundated, all other things being held constant, the more often it's inundated, the more possibility there is for the deposition of mineral sediment. And hopefully you can see just through this physical mechanism that an increase in the rate of sea level rise will tend to be accompanied by an increase in the rate of mineral sediment deposition. That's only part of the story. Another part of the story is the plants. And of course, salt marshes are as productive as tropical rainforests and that sort of thing. And so it's no surprise that properties of the vegetation have a huge influence on sediment deposition patterns. They also tend to bind the soil together through their roots. They contribute organic matter to the soil. They introduce all sorts of neat couplings between the geomorphic and ecological processes. The one that I wanted to highlight here is that in a lot of cases, especially for spartina alterniflora marshes, the growth rate of the vegetation actually tends to increase. Its annual productivity tends to increase in years of anomalously high sea level. And so now, in addition to that, just a pure physical mechanism, you now have a biological mechanism as well, where an increase in the rate of sea level rise, at least for a lot of marshes, will tend to increase the rate of plant productivity, which will contribute more organic matter, help bind the soil even more, and also trap more mineral sediment deposition. So both this biological explanation and this physical explanation suggest that there will at least be a tendency for sea level rise rates for accelerated sea level rise rates to be accompanied by increases in vertical accretion. So the salt marsh soil is going to build at faster and faster rates with faster sea level rise rates. Okay, so I wanted to show you a little bit of data that helps support that argument. There's lots of ways, there's lots of data that would support this argument. I'm just going to show one example, and that's the long-term SET record that Linda Bloom, Bob Christian, and Mark Brinson have compiled over the last 20 years now at the Virginia LTER site on the eastern shore of Virginia. And basically what they find is that the high elevation salt marshes build at about 3 millimeters per year. That's a rate of elevation change. And the low elevation marshes tend to build at 5.5 millimeters per year. I left out the middle elevations, but the middle elevations build at basically intermediate rates. And there's two observations about these rates that are important. One is that high elevation marsh is building at a rate that's almost equivalent to the rate of sea level rise. That's not a coincidence. That's evidence that marshes do in fact equilibrate towards the rate of sea level rise. The other observations that's important is that the more frequently flooded low elevation marsh is accreting at a rate that's faster than the rate of sea level rise and a rate that's faster than the high elevation marsh. So in the kind of models that the kind of model results I'm going to show you build off of these kind of observations, and they basically make the assumption, perhaps incorrectly, but they at least make the assumption that if the high elevation marsh were to become more flooded under higher rates of sea level rise, that it would start to behave more like a low elevation marsh and the accretion rates would go up. Now the graph on the right shows some sediment core data that shows the same pattern, except now instead of it being in space, it's a pattern in time where the accretion rate is accelerating through time. So some of that's due to incomplete compaction, but even if you adjust for that, you still see an increase in the accretion rate over time, suggesting that this marsh is adjusting to accelerating rates of sea level rise, like I tried to outline in those conceptual examples. This is one more piece of evidence. This is a meta-analysis of 140 different measurements of accretion and elevation change in marshes in North America and Europe. And basically it suggests that high elevation marshes, sort of the median accretion rate is something like the rate of sea level rise. I've plotted accretion minus sea level rise rate on the x-axis, and so the 0 point would be a marsh that's perfectly keeping up with sea level rise. Basically this shows that high elevation marshes, some are keeping up with sea level rise, some are not, but the median is about, the accretion rate is about the rate of sea level rise. You might interpret this to say 50% of the marshes are not keeping up with sea level rise, but that would be a really bad mistake to make. And the reason is that if the marshes, well, based on the slide I just showed you, we expect that high elevation marshes should increase their accretion rate as they become more flooded. And so on the panel on the right side of this slide now, I'm showing just the low elevation marshes. Those are the most frequently flooded marshes, and they show a different story. So now there is if you restrict the analysis to just the more frequently flooded marshes that we think are a proxy for how marshes will operate under accelerated sea level rise, we see that most of these marshes have an accretion surplus, that they're accreting at rates faster than or equal to the rate of sea level rise. Other meta-analyses have shown the same thing. I've highlighted a couple at the bottom of the screen, but there's other meta-analyses that come to very different conclusions. I guess at this point, all I want to say is that there's at least a tendency for marshes to adjust in the vertical dimension. There are certainly thresholds to that effect. We know from coastal Louisiana that marshes can't survive indefinite rates of relative sea level rise, particularly if they don't have sediment. So there's all sorts of caveats associated with this ability to maintain an equilibrium condition. Closer to home in the Chesapeake Bay, we have enormous marsh loss in the Blackwater National Wildlife Refuge. Clearly, there are thresholds. They all have to do with the ability of the plants to survive. And if the plants are unable to survive, then you lose all those ecogeomorphic feedbacks, and the system starts to run away in the other direction, where the loss of ecogeomorphic feedbacks leads to accelerated erosion and accelerated loss of elevation, which makes the plants impossible to grow back. So there are thresholds to related to plant health, thresholds that limit the maximum rate of sea level rise a marsh can survive in the vertical dimension. And I'll show you one summary of model results that tries to express that. In this slide, basically we've taken 5 leading marsh models, or at least the leading marsh models in the year 2010. These were models by myself, Andrea De Paus from Italy, Stain Timmerman from Belgium, Jim Morris from South Carolina, and Simon Mudd. And basically, we ran the models under similar conditions, and we controlled for the suspended sediment concentration and the tidal range, and we tried to predict, using each of these models, what the maximum rate of sea level rise that the marsh could survive. That's what I'm calling the threshold sea level rise rate. And what we found is that that threshold rate of sea level rise varied by at least 2 orders of magnitude, depending on the suspended sediment concentration in the tide range. But if you if you account for those 2 factors, tide range and sediment supply, then the models predict relatively cohesively a common response. And that's what I've plotted here. To give you an example of how this plays out in a real world setting, Chesapeake Bay marshes are microtidal, usually a tidal range of about 1 meter, sometimes a lot less. And typical suspended sediment concentrations I've outlined with this box, about 10 to 40 milligrams per liter, and that's fairly typical for an East Coast salt marsh. And so we would predict threshold rates of sea level rise from anywhere from about maybe 4 millimeters to about 10 millimeters for the Chesapeake Bay microtidal system. And that, of course, is right within the range of IPCC scenarios for sea level rise rates in the future. And so what this modeling tells us is that sea level rise rates, depending on how fast they are, could either be less than what a marsh can survive or more than what a marsh can survive. And it's going to depend a lot on tidal range and suspended sediment supply. If you're thinking of one of the big European estuaries or a major river delta around the world with sediment concentrations of 90, 100 milligrams per liter, even higher than that, relative sea level rise is almost a non-issue. The models predict that those systems should be able to survive 100 millimeters per year of relative sea level rise. But these microtidal sediment deficient marshes might be susceptible to sea level rise under present day conditions, sea level rise rates of 4 or 5 millimeters per year. Okay, so I wanted to show how those threshold rates of sea level rise play out on the landscape. And I'm going to use an example again from the Chesapeake Bay. The picture that I showed you on the title slide was taken right where this black circle is. My kids were standing right here, if you can see my cursor. And I'm going to show you a video that starts at the downstream end of the Blackwater River, where it empties into Fishing Bay. And we're basically going to fly in a small plane up the length of the river to the northwest. And there's a couple important things to look for and to know about the system. One is that the tide range at the mouth of the Blackwater River is about 1 meter, and by the time you get up to the upper reaches of the of the river, the tide range, the astronomical tide range is less than 25 centimeters. So strong gradient in tide range, and then there's also a strong gradient in sediment, where you have the most sediment in the downstream portions of the river. All right, so before I start the video, just think to yourself, would you expect the marshes to be healthier on this end or up here, given what you saw in this type of graph? We said the threshold rate of sea level rise should be related to the suspended sediment concentration in the tide range. And with any luck, this next slide will show a video. All right, good, here we go. So we're starting at the mouth of the Blackwater River, the downstream end. And if you look around you, you can see some tidal channels, but you don't see many ponds. There's a couple, but by and large, you have expansive marsh. As far as the eye can see, if you were looking out the other side of the plain, you would see the same thing. You would see big, widespread, expansive marshes. And that, of course, is in the region of the river where tide range and suspended sediment concentration are high, where the models predict the marsh should be stable under current rates of sea level rise. So right now, we're flying almost exactly over the pictures that I showed you in the title slide, and where I suggested was a transition point between stable marsh and unstable marsh. So if you look out that little tiny window, you can start to see some ponds forming. Those are the same ponds I showed you in the title slide, or pretty close. They've been forming rapidly over the last 50 years. Okay, the video stopped for some reason. I'm not sure why. Okay, now it's going again. It jumped ahead, but now when you look out the window, you see that there's more open water than there is marsh. It's almost completely inundated, and that section of the marsh in aerial photographs from 1937 show that the marsh was completely, there were almost no ponds at all in 1937. It was basically the only place where you didn't have marsh vegetation was the Blackwater River itself, and all the vegetation surrounding the Blackwater was intact in the year 1937. And so we've had massive loss of marsh upstream. And of course, the relative sea level rise rate from downstream to upstream, you know, ballpark, it's been the same. The big difference is sediment supply and tide range. And so just like the models, you know, the models predicted an increase in marsh adaptability with increasing tide range and with increasing suspended sediment supply, that's exactly what we see along this same gradient, where you have broken up, rapidly submerging marsh at the upstream end and much more stable marsh at the downstream end. So I think this is a good example of the models predicting, at least qualitatively, the type of behavior that we see on the Chesapeake. And we've now offered an explanation for why this marsh is stable and the marsh in the upstream portions is submerging. So we're building to that story of being able to predict why one marsh here is stable and why another marsh close by is unstable. All right, so the preliminary conclusions of this section is that marshes tend to be stable in the vertical dimension historically, but with some really important thresholds related to tide range and sediment supply, as we saw both in the models and across the real landscape on the Chesapeake, in the Chesapeake region. All right, the next section is basically tries to make the point that if marshes tend to be stable in the vertical dimension, then it stands to reason that changes in marsh size should be governed in large part by lateral processes. And there's basically two lateral processes that I'm thinking about. One is the migration of marshes into uplands, and the other is the erosion of the marsh at the seaward edge. And again, I've got some model and field examples. I'll start with the field examples. This is from the lower Chesapeake Bay, the mouth of the York River, basically where the York River empties into the Chesapeake Bay. It's right across the river from them, so it's one of our go-to study sites. And I'm going to try to show you a video in the next slide. Let's hope this works, and I think it will. All right, good. It's essentially, this is Goodwin Island. It's basically marshes and forests. The edge of the marshes are eroding, maybe by 0.5 meter per year, something like that. And so the island as a whole is getting smaller. The interior of the marsh is more or less keeping up with sea level rise. And then the upland edge is rapidly migrating. So I'm going to pause the video, I think. Nope. Let's see if I can jump back to where that was. All right, good. Hopefully it'll stay right there, because that's the picture I want to show you. The marsh that you're looking at now is everywhere in this picture. The marsh is less than 100 years old, and most of it's less than 50 years old. And this is the mechanism by which sea level rise can create marshes. This is all used to be forest, and it's now converted to marsh. And you can see, even though it's a snapshot in time, you can see all the dead trees. You can see the ghost forests out in the marsh that are your indicator that this used to be forest. Even if you didn't have the historical maps and photographs that show the migration, you can see it today by seeing dead trees and stumps out far from the modern forest edge. And so one of the interesting things about this island is, even though the island is getting smaller, the amount of marsh on the island is getting bigger, because the rates of migration into the forest are faster than the rates of erosion on the edge. And at least so far, the marsh interior is keeping up with sea level rise, so it's not contributing to much change in area. All right, so I'm going to transition from that into a numerical model that basically tries to, in a more quantitative way, express what I just showed you in the pictures. So we're going to run a transect across the marsh from the edge. The edge is going to either erode or prograde, depending on how much sediment's in the water and what the wave conditions are. The marsh forest boundary is going to move with sea level rise. As sea level rises, the marsh is going to propagate into the uplands. And then we have a dynamic marsh accretion model that simulates the interior of the marsh. I'm going to skip that slide. All right. Before I get to the model, I'll show you just a couple more examples of that upland drowning creating marshes. Not because it's hard to understand, but just because it's really fun to look at these pictures, and the process is happening all over the Chesapeake region anyway. I said this marsh here formed within the last 100 years. If you looked at the marsh forest boundary on the ground, it would look something like this, where you have a few live trees, a bunch of dead trees, and then you have a discontinuous marsh that's rapidly developing under those dead and dying trees. So this is what the current marsh forest transition looks like in the Chesapeake system. It's usually loblolly pines, often Spartina patens, and especially Phragmites that comes in under the dead trees. But in a decade or two, it'll look something like this, where now instead of patchy discontinuous marsh, you have a continuous marsh under still standing dead trees. And then in another decade or two, it might look like this, where your only indication of the forest that once was are these little stumps. And it's not uncommon at all to trip over a stump, or if you're taking a sediment core through the marsh, to hit a stump or some log that's been buried in the marsh. And then if you were to wait another 10 or 20 years after this, those stumps might be completely buried, and you would have no visible marking at the surface of where the forest used to be. But if you dig down with sediment cores or shovels, you can find it if you're, if you're in a gently sloping, low elevation area near a forest. So this is a widespread observation that we see, and I'll show you some more examples. But I want to show you the model first. So this, we talked about how the model's set up. It's a transect model for connecting the open water, the marsh interior, and the upland boundary. And these are the processes and the equations that govern each of those boundaries. Sea level rise influences all three of those processes. although it influences the upland migration and vertical accretion more than it influences the edge. I can explain that in more detail if you have questions at the end. But essentially, sea level rise will tend to increase all three of these components, and so therefore it's difficult to predict beforehand whether sea level rise will lead to bigger or smaller marshes or stable marshes, because it could potentially influence each of these boundaries. All right, so let's see an example of how this model works. And you can think of the same transect at Goodwin Island connecting water, marsh interior, and the forest. So the easiest thing to see is the forest retreating through time as sea level rises and the marsh propagates inland. I'm going to show that video again. This boundary, the edge, the seaward edge, is also eroding back. And then the marsh is building vertically through time. And actually the height of all these little green lines actually represents the biomass of the plant in the model. And I'll show it one more time. So you've got all these different boundaries moving. In this particular simulation, and this result depends a lot on the edge erosion rate and the wind conditions that influence that. But in this particular model simulation, the upland migrated faster than the edge. And so therefore sea level rise caused the marsh to get bigger. As I alluded to before, that particular behavior depends on a lot of variables like sediment supply, erosion rates, especially the slope of the uplands that the marsh is trying to migrate inland. And so I've normalized for a couple of those variables here. I've kept the suspended sediment concentration constant, and then I've explored the influence of the rate of sea level rise and the slope of the uplands. And basically the y-axis is the change in marsh width through time. So you could think of that as an expansion rate. If it's a positive number, it's marsh expansion versus the rate of sea level rise. You can also think of this through time if you're thinking of an accelerating rate of sea level rise through time. And basically what we see is that for gently sloping uplands, marshes tend to expand with an acceleration in the rate of sea level rise. And the reason that is true is that the rate of edge erosion is less sensitive to sea level rise than the rate of upland migration. So marshes tend to get bigger with accelerated rates of sea level rise. But as we learned from some of those early slides, there's important thresholds for the ability of the marshes to survive sea level rise in the vertical dimension. And once they start failing in the vertical dimension, these changes in the boundaries becomes much less important. And so at some threshold rate of sea level rise, in this particular example at about 8 millimeters per year, the marsh switches from expanding to drowning. The other thing to point out from this graph is that this ability to expand depends a lot on the slope of the uplands next to the marsh. And at high slopes, or you can think of this in cases where humans have constructed barriers to migration, then you don't have an expansion of the marsh with an acceleration in the rate of sea level rise at all. In fact, you almost always get contraction before you get drowning. So that ability for marshes to expand with the rate of sea level rise depends fundamentally on the ability of marshes to migrate into adjacent uplands. And for all the management-oriented people on the call, I think that's a really important conclusion, that sea level rise can cause marshes to expand, at least in the short term, but only if they are allowed to migrate into adjacent uplands. All right, so this is an example of a field test of the model. This again is Goodwin Island, which you saw the aerial video of. We've delineated where the marshes were, where the forests were at a bunch of different times throughout history. And what we find is that the upland migration rates, these green boxes, are increasing strongly through time, whereas the erosion rates are not. And so that is consistent with our modeling prediction that the upland migration rate is more sensitive to the rate of sea level rise than the erosion rate. And if you, instead of looking at just migration rates instead of meters per year, if you keep track of the area of marsh and the area of forest, you would see that the area of marsh has increased through time, even though Goodwin Island as a whole is contracting, because that migration into the uplands is so important. All right. Goodwin Island is only one example. You know, it's a tiny island in the scheme of the grand Chesapeake Bay. So I have a graduate student, Natalie Sheeter, that has tried to see how those patterns express themselves over the entire spatial extent of the Chesapeake Bay. So she's gone to every available T-sheet map that were generally produced in the late 1800s, 1850 to 1900 for the most part. And for every historical map, she's outlined where the marsh was, where the forest was, and where the water was, and then compared that to modern photographs. And the T-sheets are really, they're amazing. They're really high quality. And at least if you're comparing changes from 2013 to 1850, you know, that's a long period of time. So even if there is some error, you're averaging it out over a long period of time. And what she has found that is, well, before I tell you the answer, let me pose the question to y'all and just think about it for a second. Do you think marshes today are bigger or smaller than they were in 1850? In other words, is the marsh area in the Chesapeake, the area of land occupied by marshes in the Chesapeake Bay, is it bigger now than it was in 1850, or is it smaller, or have marshes stayed about the same? This is the question that I asked my graduate student, Natalie, probably once a week for the last year and a half. And she found that there are certainly areas that marshes are getting smaller and certainly areas that marshes are getting bigger. But if you average across the whole Chesapeake Bay, or if you sum up all those changes, that the answer is that marshes today occupy roughly the same area that they occupied in 1850. And you can see this play out in these maps that I've showed you. The red colors are little change, the green colors are a lot of change. And essentially, well, if you look at net change, the green is positive and the red is negative. And so up in the upper part of the Chesapeake Bay, where upland slopes tend to be a little greater, and well, there may be some other factors involved as well. But in the upper part of the bay, you tend to be losing marshes. In the lower part of the bay, you tend to be gaining marshes. Goodwin Island was from the mouth of the York River right here in the southern part of that photograph. And so this tells us a few things. One, it tells us that if you're going to consider the response of marshes to sea level rise, you better think about the ability of marshes to migrate into uplands. There was lots of erosion. I mean, we lost 100,000 acres of marsh just due to erosion over the last 150 years, but that was compensated pretty much exactly by the amount of land that the amount of marsh that was created at the upland edge. So we saw 100,000 acres of marshes were created by sea level rise as a direct response of the drowning of uplands. Incidentally, that accounts for about a third of all the marshes, a third of all the marsh area in the places that we studied were created by that process. So I think that upland boundary is really important, and again, it has a lot of management implications as well. So I'm going to conclude this section, and then I just have a couple parting thoughts about the last topic. So the conclusions from this section is that migration into uplands is more sensitive to sea level rise than edge erosion. That tends to allow marshes to expand at least under moderate rates of accelerated sea level rise if the adjacent uplands are not very high in elevation. You know, this requires a flat coastal plain environment. And it also requires no barriers to migration like anthropogenic barriers. And if you have those barriers, then our models suggested that you have almost inevitable marsh contraction because you have erosion. Erosion's almost ubiquitous, but without any migration, then there's nothing to balance that erosion. Okay, so my final conclusion then is that the ultimate fate of marshes depends in very large part on human decisions influencing sediment supply and ability to migrate landward. The sediment supply part of that argument was that threshold rate of sea level graph that I showed you in the beginning of the talk, where the maximum rate of sea level rise that a marsh could survive in the vertical dimension depended on sediment supply. Sediment supply is largely is often modulated by land use change, construction of dams, things like that. I'm not going to spend any more time on that. What I wanted to bring us back to is this idea that the ultimate fate of marshes depends on their ability to migrate landward. And I've shown you a couple examples of that already. Wanted to leave you with another interesting statistic. This comes from one of Jim Morris's book chapters that, just based on topographic arguments, estimated that there, with a meter of sea level rise, that could create up to 11,000 square kilometers of new marsh. That's if every single, that's if all the land of suitable elevation was allowed to, if marshes were allowed to migrate at will. And if they were, that would be enough to compensate for a really large fraction of existing marshland. So even if all the existing marshland drowned, and we don't think all of it will, because remember, they tend to be resilient in the vertical dimension, but even if they all drowned, then if marshes were freely able to migrate into uplands, you would only have a small loss in the total extent of marshes, and this is summed across the entire continental US. But of course, the million-dollar question is whether the marshes will be allowed to migrate into uplands. And we saw from our modeling case that if you don't allow the marshes to migrate at all, then contraction is inevitable, and they're often prevented by and revetments and berms and those sort of things at the upland edge. In reality, well, so this sets up an important dichotomy that natural marshes tend to expand under moderate accelerations in the rate of sea level rise, and defended coastlines with dikes and seawalls, the marsh tends to contract with an acceleration in the rate of sea level rise. And that's why those are the processes that lead me to this conclusion that marsh response to sea level rise depends so much on not just the rate of sea level rise, but how people will end up going about defending against sea level rise. If we build more barriers to coastal flooding, then we'll have a scenario that looks more like this. All right, so this is my conclusion slide. Marshes tend to expand on natural coastlines and can even survive rates of sea level rise up to 10 millimeters per year, given sufficient sediment supply. We saw that in the case of the York River. We saw that in parts of the Blackwater estuary, even though the Blackwater estuary is the most renowned example of a marsh that's collapsing in response to sea level rise outside of coastal Louisiana. On the other hand, we see that marshes tend to contract on defended shorelines and for very fast rates of sea level rise and or low sediment supplies. That would be the case of European estuaries, the case of Asian estuaries, where urban areas are very separate from the marsh and are separated by walls. It's also the case for like the upper reaches of the Blackwater River, where we had fast rates of sea level rise but low suspended sediment concentrations and low tide range. That marsh is clearly contracting and drowning. And so then my final conclusions then are that the Chesapeake Bay marsh historically has been relatively stable despite fast rates of relative sea level rise and microtidal. And the reason why it's been historically stable, well, it hasn't been stable at any given point. In fact, we see lots of examples of where the marsh has been lost. But historically, at least, there's been room to migrate, and so the marsh has maintained its area if you consider the Chesapeake Bay as a whole, not just a particular point. And I think that has a lot of implications for management that I'd be happy to talk about if you have questions. And I will leave you with an acknowledgements slide if I can advance it. Here it is. Nope. Here we go. Okay. So lots of people have contributed both ideas and the actual work behind this talk. I've listed several of them, but there's many others, probably even some on the phone call, that have certainly contributed in some way or another, especially with ideas. And then a number of funding number of agencies have funded the work, And then finally, since it's recruitment season, I'm trying to hire a postdoc and a graduate student. So if anybody is looking for those sort of opportunities, please let me know. Send me an email. My email address is kerwin@vims.edu. It's just my last name at vims.edu. All right, so thank you very much. Sean, I guess I'll turn it back to you, and I'd be happy to answer questions.
All right, thanks a lot, Matt. So to begin with, we do have one question in the chat box. So please, or in the question box. So please, everyone, if you have questions, please send them over to us. And that first question is, why is sediment supply closer to the ocean than upriver? Is there a dramatic increase in river velocity allowing sediment to drop out at the ocean? Or is sediment being supplied by the ocean rather than tributaries upriver?
That's a great question. And the answer to that will definitely depend on whatever estuary you're in. There's examples of where sediment concentrations sediment supply can either increase or decrease down the length of the river. In the particular case that I was discussing on the Blackwater River, the Blackwater River itself is small and the tributaries are even smaller, and it's a really pristine environment, and there's basically no sediment washing off of the watershed that enters the tributaries. So the simplest part is that there's no sediment being inputted on the upstream end. On the other hand, at the downstream end, and this wasn't really the ocean, it was a bay that a small bay that empties out into the Chesapeake Bay, but it's a shallow water bay. It's basically wide and shallow, and it's a perfect environment for wind to create waves that stir up sediment. And so the sediment source for that system is that downstream shallow bay. And when the wind's blowing, it entrains sediment, and then that sediment gets advected up the river on flood tides. But it can't, the flood tides, that's a microtidal system. The flood tides can't advect sediment very far upland, and so it results in a really strong spatial gradient in sediment supply.
Great, thanks. And we have another one. So this one is, do you know if anyone has used your models / results and compared them to other systems / observations in the mid-Atlantic? If so, what were their conclusions?
No, most of the modeling that I showed you, at least, well, the Transtech modeling, that's all pretty brand new. So they have not been applied to other places. Now, just a more general argument, the vertical accretion modeling, not specifically my model, but there's lots of spatially explicit models that have been applied to landscapes as a whole. And if you include some kind of dynamic accretion term where the accretion rate tends to increase with the rate of sea level rise, most of these models and most of the environments predicts a small increase in the marsh area with sea level rise, which is a function of basically the marsh moving into the uplands, followed by loss of marsh area in the out years of the experiments, and in the higher sea level scenarios as the marsh is overwhelmed by sea level rise. So I'm not sure that that's all really been put together and that people have specifically argued that. But I think if you were to look at it critically and you were to pick models in which landward migration was possible and you have a dynamic accretion term, I think you would find in general that for a lot of different places on the East Coast that you would find marshes tend to get a little bit bigger with a little bit of sea level rise, and then tend to get a lot smaller with a lot of sea level rise, if that makes sense. Certainly this will depend on the particular location. If you did this in the northeastern United States, where you have much more steep topography and lower sediment supply, you get a very different outcome. There you would have inevitable marsh loss. You wouldn't see the marsh expansion at all. But I think in general, I'm not sure that it's really been shown, but I think I think we will soon start to see that pattern becoming more apparent in other systems as well. I will admit that's a fair bit of opinion on my part.
We appreciate all the opinion we can get. So one more question in the box here is, says sediment supply in rivers on the east coast of the U.S. was increased as a consequence of land clearing and agriculture by European colonists. Does this mean that our current extent of marshes is larger than it would be without human disturbance? Maybe we should have less marsh than we do.
Oh, it's a great question. It's one I've asked myself many times. I try not to get into value judgments as far as whether we want more marsh or less marsh. I think bits and pieces of that question are definitely true, but it's sort of hard to come to an overwhelming conclusion. You know, my own work, I've looked at marsh expansion in the Plum Island system, and at least on one river in the Plum Island estuary, the marsh got a lot bigger in response to European settlement. It increased by 50%, I think. But that's one river in a big state. And it's not at all clear that the other rivers experience the same pattern. There's certainly lots of examples. I guess there's lots of local examples of where land use change, deforestation has caused increased sediment loads in bigger marshes. I can think of at least 4 local examples, but whether that, I am not ready to say that that's happened everywhere and that the gain in those local examples is relevant to the whole marsh area. I think the person that's asking the question is on the right track. You know, but that's an important question. You don't want to you don't want to give a simple answer that without being really sure.
All right, thanks a lot. We got another one coming up, which is, can you recommend more practical versus the philosophical one that was last asked, but can you recommend a simple sea level rise model that may be used as a preliminary step to predicting marsh migration, accretion, upland losses, etc.?
Oh, okay. Assuming that you're talking about a spatial model that represents that can be applied to a real landscape, then there's several options. Starting with the worst would be a bathtub model, which has no ecogeomorphic processes in it at all, no ability for the landscape to adapt, but it will tell you it will sort of tell you what areas are most vulnerable. So that would be the simplest. SLAM goes a little bit further, depending on which version of SLAM you use and how much you know about the specific site. I think the important thing in any model that you apply is that it should have a dynamic accretion rate where there is the ability of the accretion rate to increase as the marsh becomes more flooded. That's Marsh Geomorphology 101. That's the most important feedback that you should include. Some versions of SLAM do incorporate that feedback, and so those versions of SLAM would be appropriate to use. Jim Morris has a version of the MEM model that is spatially explicit and can be used to do this mapping or to do this sea level rise simulations. There is another model called Warmer that's been applied a lot on the west coast. It's developed by USGS. That also has, you know, that key ability of the marshes to accrete faster under rates of sea level rise. And then, you know, I have versions of mine that I'm applying on real landscapes as well. So, you know, I think any of those is fine as long as you have enough data. Really, the limiting factor is not the model; it's the data that you have to be able to parameterize the model and ensure that you understand how accretion rates will change. At the end of the day, that's one of the critical limitations. Is you have to know you have to have some idea what that maximum rate of accretion is, and even better, how that varies across a spatial landscape. And I think the others don't necessarily do a good job of how the accretion rate would change with different distances from the channel, for example. Some of my latest models do that. So anyway, that's what, five examples of models you could use.
Great. The questions keep coming.
Good.
So over the long term, with continual sea level rise, it seems that there will inevitably be more anthropogenic upland hard barriers, leading to greater loss and accretion. Can you speak to this and any analysis you may have done to land use?
I don't see a direct link between human barriers to migration and accretion. I suppose the best example of that would be not a barrier to marsh migration, but like armored shorelines, for example, where the rocks are put on the seaward edge of the marsh, not the landward edge. That would reduce the amount of sediment that's liberated through erosion and perhaps limit the ability of the marsh to accrete vertically. That's sort of a specific response to the way the question was worded, but I think the more general goal of the question was, will we start to defend coastlines more under rates of accelerated sea level rise? And, I don't have a good answer for that. Y'all, probably everybody on the call has as good of an opinion on that as I do. Right now, the Chesapeake, for example, even though we have lots of urban areas in the Chesapeake, like Baltimore and Norfolk and Hampton Roads, there's still a lot of rural areas, and it will never be practical to fence off or build a wall around the eastern shore of Virginia. It's not a system that's, it's not valuable. The land's not valuable enough to protect. 2/3 of Virginia is forested. It's hard to imagine defending a forest by building a wall. If you just build a little berm, oftentimes you still lose the forest because you have saltwater intrusion that goes underneath the berm through the soil. So I don't think it's a foregone conclusion that future flood defense measures will eliminate the ability of marshes to migrate. Certainly the limits, they'll reduce the amount of land available to migrate, but they'll still, I feel confident that for the foreseeable futures, there'll still be rural sections of our country. A lot of our marshland in the United States is in relatively rural areas. I mean, coastal Louisiana is not a metropolis by any means, even if New Orleans is. And so, my general opinion, and again, this is just an opinion, is that there is lots of rural land adjacent to marshes that is economically not in a position where it doesn't make sense economically to defend that land against sea level rise.
Great. So on top of that, it sounds like basically one of the biggest things is just not to provide barriers to marsh transitions. But what else do you think are the most important kind of management questions that we see focusing on coastal wetlands, whether it be dealing with sediment issues in terms of dam removal, dealing with freshwater flows and nutrient loading, and in some cases even assisted plant migration? Would you like to talk at all about those kind of management ideas?
I'll try to talk a little bit about it. I think you're right that the big one, as far as I'm concerned, is providing space for the marshes to migrate. And really, that doesn't even require a management action. It simply requires not doing a management action, if that makes sense. If you do nothing, the forest will convert to a marsh eventually. You don't have to help it along. It'll do it. So, my opinion is you just try to keep barriers out of the landscape as much as possible, or don't build new ones. That sort of thing. More generally speaking, when other ways to combat sea level rise, as far as other ways to enhance marsh resilience to sea level rise are dam removal that increases sediment supply. That's obviously going to be a really local thing depending on whether your rivers are dammed and whether they have a lot of sediment to begin with. There's thin layer dredge disposal, which works really well for a small area, but is hard to imagine doing on a real big scale. There's issues with eutrophication and how nutrients affect the stability of a marsh. Coastal Louisiana, is a great place to look, since they're basically trying all of the above to restore the wetlands of the Mississippi River Delta. They're relying on a combination of increasing sediment supply by adding diversions to the Mississippi River so that the water can flow past the levees and into the receiving basins to build marshes back up. I think that's a great example of something that can be done at a large scale, at least if you have a large river like the Mississippi. But they're supplementing it with targeted dredge spoil deposits, where they're picking a spot where they want to build a marsh, and they just build the marsh by dumping enough sediment right at that given spot. I think the wisest use would be to do both of those at the same time, where you pick spots to build the marsh from dredge disposal, but you do it in places that will help capture more sediment from the river diversions. I think that's a really good strategy. I don't know. There's lots of options. Probably one option is going to be better in one system, and another option is going to be better in another system. Out of all of those options, I think the migration of marshes into uplands is the most likely to occur at really big spatial scales.
Okay, great. Well, I'm going to give a couple announcements for the next few webinars, and if anyone has any questions they'd like to put in the meantime, then we can talk about that as well. But
let me say, I'd love to hear from anybody if they have feedback on any of these ideas, or if you're a prospective postdoc or graduate student or no one, please send me an email. Let me know. Giving these presentations is so much more fun when you can interact with the audience. So since we haven't really had that opportunity, just send me an email if you have some thoughts. I'd love to hear from you.
Thank you so much, Matt. Thanks everyone for coming, and again, send a question in the last few minutes. We've got a lot of thank yous on the questions box here, Matt. But if we could advance the slides, yeah. So look forward to our next webinar, which is by Andy Erb from Alpine Eco. So it's on November the 16th at 1 p.m. We hope to see you there. We're always looking for future webinar presenters and topics. So if you're interested in presenting an SWS webinar or have a topic of interest you'd like to see us cover, please indicate this in the evaluation survey you will receive after the conclusion of the webinar. And the next conference is in Denver. So please, they're saying it's never too early to save the date. Join us May 29th to June 1st, 2018 in Denver, Colorado for the 2018 SWS annual meeting. The deadline has been extended for symposium and workshops to October 30th, so there's still time. Visit the meeting website for more info. The application for the SWAMP 2018 is officially open. So do you know any student who may be interested? Visit the Multicultural Mentoring Program page for more information. And lastly, thank you, Matt, for taking time out of your busy schedule to present an SWS webinar. It was really enlightening. Thanks very much. And it looks like all of the rest of the comments are still just thank yous. Oh, and they're asking for your email as well, which is...
Can I try typing it into the question box? I don't know if it'll work.
Yes, or we can email it afterwards.
All right, I just clicked the send to all button. I don't know if it worked or not.
Okay. I'll type it into this question box, but we should probably. Do you want to just tell everyone out loud real quick?
Sure. Okay. It's kerwin@vims.edu, and if you're looking at the same screen I am looking at, then the last name Kerwin is on the screen, so you can see how to spell it. KIRWAN at VIMS, Virginia Institute of Marine Science .edu. So kerwin@vims.edu.
And after all that, it sounds like everyone did get it. So
okay, even better.
Yeah. All right. Well, thanks everyone, and hopefully see you next week. Thanks again, Matt.
All right. Thank you, Sean. Bye, y'all.